All right. So the first thing that we want to talk about is what does this word empirical means? And really there's kind of two definitions for empirical formula that we want to become familiar with. All right. The first definition is given in the very first statement here. The empirical means based on evidence. Okay. Or you can think of it as being based on data. All right. So if we were normally in school, we would be doing actually 2 empirical formula labs where you would be doing some sort of reaction where you put 2 reactants together, you form one product, and then we'd be able to actually calculate the empirical formula from your data. All right. The empirical formula is the simplest whole number ratio of the atoms present in a molecule. So that's kind of the second definition there. Okay. So based on data, and then simplest whole number ratio is the second definition there. You're going to want to be able to recognize both of those definitions, okay? Because it's defining characteristics of empirical formula, okay? So we're going to talk about kind of the 3 steps that we're going to take in order to find empirical formulas. And we'll start this by writing down these steps together here, okay? So the first step is going to be something that you're familiar with, which is a conversion. So you're going to convert the masses that are given to you for elements to moles for each element. All right. I'm going to add a little parenthesis in here because sometimes percents will be given to you. And if they are given to you, you're just going to change that percent to grams. Will problem that has the percents, so you'll see exactly, hopefully exactly what I mean here in a few moments. Okay, so our first step really is what we've been learning for the past about a week now, okay? Converting mass to moles. Right. Already I'm trying to think what conversion factor would I be using here? I would be using molar mass. All right, let's talk about step number 2. Step number 2 is divide all the moles by the smallest mole amount. Okay, so most often we're going to see either 2 or 3 elements here, okay, in our empirical formulas. So you're going to have, 2 or 3 numbers to compare. All right, and you're going to want to divide all of the mole amounts by the smallest one. Okay, now we get to step 3. We kind of have 2 different circumstances here. All right, if all the numbers after your division are whole numbers or really close, and we'll we'll kind of see some examples of this like really close idea today. All right, that is how many atoms there are in the formula. So what that means is you're done. You're ready to write the formula, okay? Those numbers are going to become the subscripts in the formula. All right, all the numbers are whole numbers. Easy peasy, we're done. If we have not all whole numbers, okay? So if any answer is, do like an underline, 0.5. So what that means is a blank 0.5. So it could be 0.5, it could be 1.5, it could be 2.5, it could be 3.5, okay? Or really close to 0.5. Then we have to multiply all numbers by 2, so they're all whole numbers. All right, so what I'm gauging from this is that we cannot have fractions or decimals, whatever way you want to think about it, as subscripts in your formula. Okay, now we honestly have not seen a lot of formulas, right? We've talked about water, we've talked about carbon dioxide, maybe like hydrogen peroxide, H2O2. We haven't seen a ton of formulas, but from the formulas that we have seen so far together, you would probably be able to recognize that you've never seen, H 1.5, O 2.7. We've never seen decimals in our formulas, okay? And so really you want to think about the fact that those numbers are representing the atoms in the formula. You can't have a fraction of an atom. It just doesn't work that way. All right, so those are our steps. Let's go ahead and dive right into a problem and figure out how we're going to do these steps and make sure that we are, capable of doing these steps and understanding the directions. All right, so we'll go ahead and take a look at the first example I have here. Find the empirical formula of a compound containing 4.9 grams of magnesium and 32.0 grams of bromine, okay? So I'm going to follow my directions, and my first step is to convert the mass to moles for each element. Okay, so you should be pretty familiar with this, pretty confident with this, so let's do it. So we'll start with our 4.9 grams of magnesium. Over 1. Again, I'm thinking I'm converted to moles, so I'm going to use molar mass. So I'm going to have out my periodic table. Once I find magnesium on the periodic table, I'm going to round its molar mass to 2 decimal places. So I'm going to round that to 24.31 grams of Mg on the denominator so that my units cancel. And then 1 mole of Mg in the numerator on the top, because that's what I'm trying to convert to. All right, I'm thinking about that 4.9, and I'm thinking that there are 2 significant figures. So my answer should have 2 sig figs. When I divide out, I get 0.20 moles of Mg as my answer here. I do the same thing with my 32.0 grams of bromine. Bromine is Br. So we'll set up this conversion. All right, bromine's molar mass rounded to 2 decimal places is 79.90. And we'll put 1 mole of Br on the top. That's our definition of molar mass, right? 79.90 grams of bromine is equal to 1 mole of bromine. Notice here that we've got actually 3 sig figs. 32.0 has 3 sig figs. So this answer should have 3 significant figures. When I get my answer, I can round it to 0.400 moles of Br to have my 3 sig figs there. All right, so now we're looking at step number 2. Step number 2 says divide all the moles by the smallest mole amount. So what is smaller here, the 0.2 or the 0.400? 0.2, yeah, absolutely. So I'm going to divide this by 0.20, and I'm going to divide this by 0.20. Okay, whatever one's smaller, no trick here. All right, when I divide 0.20 by 0.20, I get 1. And when I divide 0.400 by 0.20, I get 2. These numbers are both whole numbers, okay? So now I'm looking at step 3a. It says if all the numbers are whole numbers or really close, that is how many atoms there are in the formula. So what this tells me is that I can now write my formula, and my formula will be Mg1 Br2. Is there a different way to write this formula that you are aware of? MgBr2, correct. We do not necessarily need that 1. Right? It's kind of assumed there that that silent 1 is there. Whatever way you're more comfortable writing it, I don't mind if you keep the 1 in there, but you don't necessarily need to have it. All right, so this is our empirical formula. Right? Questions or concerns, guys, on anything in that process there? All right, let's take a look at our second example. We're going to run into 2 different things than we have in our first example together. All right, so it says find the empirical formula of a compound that is 70.0% iron and 30.0% oxygen. So if we go back up to question or step 1 in our directions, it said if percents are given, just change the percent to grams. So this is going to be 70.0 grams of iron and 30.0 grams of oxygen. Now that I have that, I feel like I can dive right into step 1, which is converting these grams to moles. All right, so let's start with our 70.0 grams of iron. All right, iron molar mass rounded to 2 decimal places is 55.85. And like always, we'll have our 1 mole of iron on the top. All right, I'm looking for 3 sig figs when I divide this out. And I get 1.25 moles Fe. All right, let's do the same thing with our 30 grams of oxygen. Oxygen's molar mass around 2 decimal places comes out to be 16.00. And 1 mole of oxygen on the top. Again, 30.0 has 3 sig figs, so I'm looking for 3 significant figures in my answer. Divide that out, I get 1.88 moles of oxygen. All right, which one's smaller, 1.25 or 1.88? 1.25. All right, so we're going to divide both by 1.25. All right, so 1.25 divided by 1.25, easy peasy, that's 1. 1.88 divided by 1.25, not as easy, 1.504. Okay. I recognize right off that this is not a whole number. So I'm going to skip down to 3b, and 3b tells me if any answers are 0.5, so I've got a 1.5 here, then multiply all numbers by 2. All right, guys, this is the biggest mistake. You recognize, again, multiply by 2 because it's a decimal, but what students forget to do is also multiply every other number that you have there by 2. It's that math property. Whatever you do to one side, you got to do to the other side. Okay? When I multiply 1 times 2, I get 2. And when I multiply my 1.504 by 2, I get 3. All right? So now these are numbers that I'm going to use in my empirical formula. So my empirical formula then becomes Fe2O3. All right, questions or concerns, friends, on anything in that process there? No? Everybody's okay? All right, so part of your assignment today is going to be to do the next 2 problems. We're going to skip over them for the time being to come down to talk and take our notes on molecular formulas. Okay. Empirical formulas and molecular formulas are heavily related, which is why we're talking about them both, kind of 2 new topics in one day. So here's the definition of molecular formula is the actual formula, not the simplest ratio. All right, so I want to show you an example of this before we take our notes. So C6H12O6, we've actually talked about this before. This is glucose. This is the molecular formula for glucose. All right, what you might recognize here is that it is not the simplest ratio between those atoms, right? 6, 12, and 6, I could reduce those numbers. All right, In fact, if I chose to reduce those numbers, I would probably divide them all by 6, so I would get C1H2O1. And this would be your empirical formula. Okay? What I want you guys to see from this example is that your molecular formula is going to be a multiple of your empirical formula. There is going to be some sort of relationship between the empirical formula and the molecular formula. All right? And we're going to talk about what that relationship is as we go through our directions here. All right, so step number 1 for finding your molecular formulas is to find the empirical formula. You just learned that. Should be, all right, find the empirical formula. Nothing too crazy yet, right? The second step is to find the molar mass of the empirical formula. All right, we've been doing molar mass now for like 2, maybe 3 weeks. So we should be pretty confident about being able to find the molar mass of the empirical formula. All right, step number 3. Here's where things get a little bit new to us. Okay, the problem will tell you the molar mass of the molecule. Okay, take this given mass and divide it by the molar mass of the empirical formula. All right, so we already kind of hinted at the fact that the molecular formula is going to be, have some relationship to the empirical formula. And here's where the relationship stems, okay? We are going to take the given mass, which is the molar mass of the molecular formula, and divide it by the molar mass of the empirical formula. And that's how we're going to figure out the ratio between the two, okay? With this asterisk here, I want you to fill this in. This should always be a whole number. All right, so what that tells me is if I do this division of masses, I don't have a whole number. Perhaps I calculated the molar mass of the empirical formula wrong. Perhaps I just wrote down the mass from the problem wrong. Perhaps I found the wrong empirical formula. Okay, so it's kind of like a check and balance for you before you solve out the rest of the problem. All right, step number 4 is to multiply the subscripts in the empirical formula by this number to get the molecular formula. All right, guys, if you missed any of these notes or I was going too fast, my note sheet, the first document in our assignment today, has all of these notes typed out for you, okay? So if you missed something or just need to reread something later on, you can go back to that. All right, friends, let's go ahead and do an example. Go ahead and do this first problem right below our notes. So it says a compound composed of hydrogen and oxygen is found to have 0.59 grams of hydrogen and 9.40 grams of oxygen. The molar mass of this compound is 34.0 grams per mole. There's that given molar mass, okay? Find the empirical and molecular formulas. Okay, so the first step here is to find the empirical formula. So I'm going to refer back to the front page, look at my notes. I need to convert from grams to moles to begin this, okay? So let's start with our 0.59 grams of hydrogen. Finding hydrogen's molar mass, I'm going to round it to 2 decimal places. It's going to come out to be 1.01 grams of hydrogen. And we're going to have 1 mole of hydrogen on the top because I'm converting to. I'm looking for 2 significant figures in my answer here. So I'm going to be looking for my answer comes out to be 0.59 moles of hydrogen. All right, we've got to convert our 9.40 grams of oxygen next. When I take oxygen's molar mass and round it to 2 decimal places, it comes out to be 16.00 grams of oxygen in the denominator there, and then 1 mole of oxygen on the top. (9.40) has 3 significant figures, so I'm looking for 3 significant figures. When I divide this out, I get 0.588 moles of oxygen. All right, guys, so step number 2 now in our empirical formula is to divide by the smallest mole amount. Which one of these is technically smaller?
Tough call.
Tough call. They're close. 0.588? Yes, that is the smallest one. So if we divide both of these by the smallest mole amount, 0.588, what's going to happen? This is actually going to come out to be just around 1. And we know that 0.588 divided by 0.588 is going to come out to be 1 as well. This will happen. Sometimes you'll come out with the same subscript for your elements in your empirical formula. All right, so this means that our empirical formula is going to be H1O1 or HO. Because I am solving for empirical and molecular, I'm going to put a box around this and label this as empirical. And that is a habit you want to get into so that I know that you know what you're talking about. All right, so we've done the empirical formula. Now we need to look at our molecular formula notes. We did part 1. Part 2 says find the molar mass of the empirical formula. Okay, we can do that. So we've got 1 hydrogen and 1 oxygen. So hydrogen's molar mass is 1.00794, plus oxygen's mass is 15.9994. When I add those together and round 2 decimal places, I get 17.01 grams per mole. All right, so I can go ahead and it's going to kind of like draw a little line here and label that as molar mass of that. All right, what's my next step? It says I need to take the given mass in the problem and divide it by the molar mass of the empirical formula. Okay, what was the mass they gave us? The 34.0, yes. All right, so let's take our 34.0 and divide that by my 17.01. Wouldn't it be 2? Yes, it is. It does come out to be 2. All right. My last step. Multiply the subscripts in the empirical formula by this number to get the molecular formula. Okay? jobs are really easy because both of our subscripts in our empirical formula are the same. So when I multiply 1 by 2, I get 2. So my molecular formula comes out to be H2O2. And as we said, as we said earlier, we want to just label this as the molecular formula. All right, friends, questions or concerns on anything in this process? It's a long process, all right? There's no denying it. There's a lot of math, but I think once you practice it a handful of times, you'll have hopefully have some confidence with it. All right, questions or concerns on anything so far?